sections that were done by 3 groups of students. So, one did on crushers, the other group did on grinders and mills, third group did on fine grinding equipment. Just kind of put them all together. So, welcome to this lecture in our course on mechanical operations. In the last class, we started discussing size reduction as a mechanical operation, and we in particular looked at the laws of energy usage in size reduction. We looked at the different laws that have been derived by Kick, Bond, Rittinger. We also looked at the general energy equation for size reduction. I think it's important to have a conceptual grasp of how size reduction happens. However, to really appreciate the process, you have to see how the size reduction equipment actually look in industry, because the thing that will really impress you the most is just the scale of the equipment. These are large equipment, right? And a lot of the theories that we are talking about are only of limited use and applicability when you go to industry. If you are doing a ball milling experiment in a laboratory, you may be able to get data that fits pretty well with theory, but once you go out in industry and start working with the huge pieces of equipment and extremely large throughputs, you will quickly realize that the theories that you study only have limited use, and a lot of what's done in industry to kind of manage these equipment and optimize them is based upon very empirical data. People collect data on a daily basis, examine the data, and then react based on the data that they are collecting. But these are really the workhorses of many industries, and they do a decent job. So, we will talk about crushers first. So, as we were describing yesterday, a crusher takes large particles and reduces them to manageable sizes, large rocks into small rocks, and so on. So, crushing itself is a process of transferring a force amplified by mechanical advantage through a material that bonds together more strongly than those in the material being crushed do. So, crushers hold the material between 2 parallel solid surfaces, and they apply sufficient force to bring the surfaces together and exert energy or do work on the particle to break them into pieces. And they are classified into primary, secondary, tertiary and quaternary crushers, widely used in many processing industries. So, this is important to give you the sense of scale. You can see that there is a person standing in front of this crushing equipment, and you can see how the equipment dwarfs the person. So, huge equipment. There are 4 types of crushers that are principally used: the jaw crusher, gyratory crusher, cone crusher and impact crushers. A jaw crusher, as shown in the diagram, it works like your jaw when you are chewing something. It is a set of 2 jaws, one is fixed and the other moves back and forth. So, they are, as you can see from the diagram, the jaws are further apart at the top than at the bottom. So, it is kind of a tapered passageway, and the particle moves down and it is sequentially crushed to smaller and smaller sizes, so that by the time it gets all the way down to the bottom, the size is just large enough to escape through the opening that is provided at the bottom. So, this is kind of how a jaw crusher works, as you can see from the animation. So, jaw crushers are used in mining, metallurgy, construction industry, chemical industry, road building, railways. Usually manganese steel is used for the jaw phases. Crushing is a highly intensive process. So, you need to make sure that you use materials that are resistant to, particularly to abrasion, erosion, breaking, damage. The size reduction ratio is not huge. You are not going to go from millimeter sizes to micrometer sizes. You will go from typically from a few centimeters down to a few millimeters in size. A cone crusher looks like this. So, this is considered a secondary crusher. It takes input from a jaw crusher and then does subsequent crushing. And so, here you can see that the material is basically being fed in through the top, and this also relies upon, it is basically a cone shaped chamber, and there is an eccentric rotation that is provided to a crushing device that is in the center of the cone, which then impacts the particles as they are swirling around and does a size reduction. Now, in this case you can see that the discharge is actually through a large opening and the feed is through a small opening. So, it is kind of, the operating principle is almost the exact reverse of a jaw crusher. So, clearly in a cone crusher you are not going to get huge size reductions, you are not going to go from a very large boulder size to small rocks. So, it is not considered a primary crusher, it is considered a secondary or tertiary crusher based upon the application that it is used in. It has certain advantages, particularly the high productivity. Because the output is not constrained, you are not going to get clogging. One of the big problems with a jaw crusher is frequently particles will get stuck in the small opening and you have to go and poke them and to loosen them, and sometimes you have to manually break the particles that are getting stuck in the outlet so that they can make their way through the outlet. So, some of these problems are avoided in a cone crusher, and it is a cost effective equipment, and again the applications are in mining, aggregation, demolition, industry, construction, environmental and so on. A gyratory crusher is very similar to a jaw crusher, except that the jaw itself, one of the jaws is fixed and the other one gyrates. In a regular jaw crusher, one of the disadvantages is that the size reduction is not happening continuously. Kind of, to some extent, it depends on when a particle gets caught between the moving jaw and the fixed jaw. In a gyratory crusher, you are constantly providing a gyratory motion to the jaws, so that the size reduction process tends to be fairly continuous as the particles make their way down. And this is what a gyratory crusher looks like. Again, pretty large equipment, lot of moving parts. One thing about use of crushers in industry, they do lead to a lot of downtime, because you are trying to crush very large particles, very hot particles. Frequently there are problems like damage to the surfaces that are coming in contact with the particles, and there are also stoppages due to plugging of the pathways and so on. So, crushers are high maintenance equipment. So, the main advantages is elimination of particles escaping size reduction. When you do a gyratory process, the likelihood that every particle will get crushed is higher than if you have a process that just relies upon eccentric motion of one of the jaws. But there are some issues with it in terms of excessive wear can happen, and because the problem again is you are kind of increasing the time of contact between the crusher and the particle in a gyratory crusher. The advantage is every particle will get crushed. The disadvantage is the crushing can be excessive and it can also be very non-uniform. So, impact crushers on the other hand again are considered secondary crushers. They use impact. They work best when there is a pre-existing defect in the material. If there is a crack or a fissure in the feed material to begin with, if you hit it with a hammer, it is very likely to fragment along the fault line. It takes a maximum feed size of 300 to 500 mm. It is a customizable crusher. So, you can basically look at the feed material and design your crushing impact operation around the features of the material. So, there are horizontal shaft impactors and vertical shaft impactors, and they differ essentially in the way that the feed material is introduced into the impact chamber. So, the feed can be either introduced horizontally or vertically, and clearly each one has its advantages and disadvantages. The main concern with a vertical feed would again be that there is a possibility of escape. Particles can go right through the impact crusher without ever experiencing an impact, whereas with a horizontal crusher your residence time is much longer. In fact, it is conceivable that the particle can get into a little recirculation flow or a stagnation region, and it can have very long residence times within the crushing chamber, and that can lead to significant size reduction. In a HSI, I mentioned that in typically size reduction equipment we try to control the maximum size rather than the minimum size, but at the same time we would like to have some level of control over the minimum size, and that is sometimes difficult to achieve in something like the horizontal impactor, because depending on the airflow and the relative position of the particle in the airflow, the residence time can differ by a great extent. It can go from very small residence time to very large residence times, and the crushing efficiency in this case would be basically proportional to the time that the particle spends moving around in the chamber and getting impacted. So, these are some references from which this material is taken. So, let us talk about grinders next. Grinders come after crushers. So, you have primary, secondary, tertiary, quaternary crushers, and after that you get into grinders. You really do not want to introduce very large feed into a grinder, because it is not designed to work on large particles. So, it is for producing very fine particles through attrition and compression. It is generally applied after the crushing operation, but it can reduce particles down to micrometers, and in fact as we saw in one of the earlier presentations, there are what are known as high energy ball mills that can actually change the chemistry of the particle. It can even produce nano dimensional particles with sufficient milling time. So, grinding is used for many purposes. Primary purpose is surface size reduction. It can also be used to increase the surface area of a solid. So, particularly in applications like catalysis, what you would like to do is maximize the amount of surface area that is available for a given volume of material, because many catalyst materials tend to be very expensive. Grinding is a way, when it is done in a very mild fashion, you can actually use a grinder just to roughen the surface, right, and when you roughen the surface, that actually increases the surface area. So, in its simplest or mildest form, a grinder, particularly a fine grinder, can just ride on the surface of a particle or any solid and just produce a very controlled roughness on the surface, and that is an application that is used particularly in industries that depend upon the increased surface area. The other reason for doing this roughening of the surface is, as we have seen before, a very smooth surface is also a very sticky surface. So, in certain machinery, particularly for example in power plants and so on, where you are flowing solid materials through a pipeline and you want to minimize sticking of particles to the pipe walls, the fine grinding is used as a way of slightly roughening the surface, so that the tendency of the particle to stick to the surface during the flow is minimized. Manufacturing of a solid with a desired grain size. Again, as you go into materials, there is a strong correlation between grain size and many of the physical properties of a material, and frequently you want to control that grain size, and grinding is a process that you can use for that purpose as well. So, there are many applications in industry, in food processing. So, what are some types of mills? Hammer mills are used to reduce particle size from a crusher. Essentially the way this works is you have hammers that are actually mounted inside a chamber, and as the particle flows through, they are subjected to repeated impacts from these hammers that are typically attached to a rotary machinery within the chamber. So, a hammer mill works by the principle of direct contact between the hammer surface and the particle whose size you are trying to reduce. Now, clearly it is a process that will work when you have high concentrations of solids, but if you have a dilute suspension, a hammer mill is not going to be terribly efficient, because the probability of impact between a hammer and the particle is going to be inversely dependent on how many particles are packed per unit volume of the fluid. In a hammer mill, again, what you are relying upon is maximizing the time that the particles spend inside the chamber, so that you can make sure that every particle is subjected to at least one or more hammer impacts. Benefits are, compared to a ball mill, which we will talk about next, it does require less maintenance. In a ball mill, you will even see it when you do the experiment, the balls tend to get worn very fast because of the mechanism. Basically the ball is not only in repeated contact with the material that it is trying to size reduce, but balls may be coming in contact with each other, which is not going to happen in a hammer mill, and the balls are also going to be coming in contact with the walls of the milling chamber, which again causes them to get degraded. Whereas in a hammer mill, the only contact that the hammer would see is with the particle whose size you are trying to reduce. So, the potential for damage to the hammer is very small. So, this is again more pictorials of how a hammer mill works, and in fact you can see that the interior of a hammer mill is designed in such a way that the particles are essentially circulated in a very small volume in the vicinity of the hammer to maximize the probability of contact between the hammers and the particle that you are going to try and size reduce. A roller mill, on the other hand, essentially the way this can work is you have two rollers and the particle gets caught between them. So, as the rollers rotate, and typically they rotate in a way where they are always rotating towards each other, the particle that is caught between them will get crushed or ground to a smaller size. And in fact, there are two types of roller mills. I mean, they basically work on the principle of compression. The particle gets caught between the rollers and gets compressed. Now, the rollers themselves can be smooth or they can have grooves. A smooth mill works simply by compression, but if you have rollers that have grooves cut into them, you can actually bring other mechanisms of size reduction into play as well. In fact, the groove can actually act as a cutting mechanism as well. So, in addition to compression, you can have some effect of cutting or slicing of the material by the grooves that are machined into the roll. The roller mill is it's a good continuous throughput device. You keep feeding material at the top, goes through rollers, and the discharge comes down at the bottom. So, it is a process that can be very easily designed to operate in a continuous mode, whereas many of the other processes, particularly the ball mill, even though in principle it can be run as a continuous process, it is difficult to design it that way. So, batch ball mills are most often, even in large capacity processes, they are run as batch equipment, whereas a roller mill can be easily adapted for continuous operation. An attrition mill, so again what you have here are discs. You have rotating discs with flat faces or grooved faces, and particles are abraded by being caught between the faces of these. These are typically used for soft particles. So, if you have a very hard metallic particle, it probably will not work well because the particle is more likely to damage the disc than the other way around. Ceramic particles, on the other hand, can be size reduced through attrition mills, because even though ceramic particles are hard, they are also very fragile. So, they break easily. And if you take a ceramic piece and drop it on the floor, it will shatter, even though its hardness is very high, because it is also a very brittle material. So, a brittle material can easily be size reduced through an attrition process. Actually, it is very easy to size reduce a ceramic particle. hammers, impact crushing works well. In fact, the other technique that we had discussed earlier, which is size reduction using ultrasonics or acoustic fields, again works very well with ceramic particles because they combine hardness and brittleness, and that is the ideal combination for size reduction. Now you can imagine if you take a plastic particle and you try to size reduce it, it's very hard, right, because it's very soft. The only thing that may work well is cutting, which is why cutting is also a very important mechanical operation. But if you are trying to compress a plastic particle, probably won't break. If you try to hammer it, won't break. So soft particles actually are very difficult to size reduce compared to hard particles, even though that may seem counterintuitive, and processes like attrition milling work really well for those types of materials. So diagram of how an attrition mill works. A tumbling mill is the one that you will work with in your mechanical operations lab next semester. So the way this works is you have a shell which is a cylinder in shape, and you fill it with the media that you use for doing the grinding, and it's being turned about its horizontal axis. So as it turns, the particles are getting carried to the top and then they drop, and as they drop, they impact the particles whose size you are trying to reduce, and they reduce the size using that mechanism. So they can be continuous or batch. The medium itself, you can have rods, you can have chains, you can have pebbles, metal balls, rubber balls, ceramic balls, virtually any material that you can fill the chamber with, and which can cause size reduction to happen through impact, can be used as the medium in a tumbling mill. So the way this works, as the mill rotates, the media gets carried to the top and then it drops. So obviously the speed of rotation of the mill is a very critical parameter. If you rotate the mill too fast, then the particles will start centrifuging. They will never drop, they will just keep going round and round along with the rotation of the chamber. So you have to design the speed of rotation in such a way that the media get carried as far as possible to the top of the cylinder and then they drop. So there is something called a critical speed, which we briefly looked at in the previous lecture, and if you design the mill to operate at the critical speed, ideally the particles will drop exactly at a 90-degree angle, which will maximize the energy of impact on the particle. Now in reality it is very difficult to control it that way, so most ball mills are operated with a safety margin. So you will calculate the critical velocity and operate the mill at about 25% of the critical velocity, and so that you do not have a lot of wastage due to this centrifuging operation. Grinding ball mills can operate in dry mode or in wet mode, and there are again advantages and disadvantages to both. The primary advantage of wet ball milling is that it prevents reattachment of fragmented particles, because the liquid medium acts like a buffer and prevents particles from reagglomerating. On the other hand, that same factor also reduces the efficiency of the mill, because the force of impact between the media and the particle is also now being buffered to some extent by the intervening liquid medium. So the size reduction effectiveness will actually be reduced when you have a intervening liquid medium. So it's kind of a balance that you need to reach. So this is how a tumbling mill looks. I mean, this is not how the ball mill in our laboratory would look. It's a nice clean cylindrical enclosure, but in industry this is how a typical ball mill would appear. So again, the mechanism is you have media mixed with particles whose size you are trying to reduce, rotate the chamber, the media go to the top and then drop down. So you can do a quick calculation of the critical speed of the ball mill. You know how you calculate this. So if this is your ball mill and you have these media and it is being rotated with some speed omega. If you want, let us say that this is alpha and your media is here, the gravitational force will be acting this way, but there will be a centrifugal force. So, these two forces will be balancing each other. So, mg times cos alpha will be equal to m times its the rotational linear velocity u squared divided by, if this this is your chamber and the radius of the chamber is some capital R and the radius of the ball is some small r, then the distance of separation between the centers of gravity will be r minus r. So, that is the force balance that you work with. Now, in the case where you reach critical speed, this will be alpha will be equal to 0. So, at critical speed the ball will drop when it comes here. So, mg will be equal to m times u c squared over r minus r, or cancel this. So, u c will be square root of sorry is that correct? Mg cos alpha equals mv squared by r minus r.
So that gives the frequency.
True, I mean uc will be equal to 2 pi omega, right? So, omega will be 1 over 2 pi times
Into r.
Hmm?
R minus r.
Okay, anyway, just look into that. I think you should get this expression that it should be equal to 1 over 2 pi times square root of g divided by r minus r. What is the expression for centrifugal force?
Into r minus r is equal to u is r omega. Omega is 2 pi here.
Oh, okay. Okay, that's where it comes from. Sorry. Okay, then it becomes uc equals 1 over, or omega will then be equal to 1 over 2 pi times square root of g by r minus r. So, this gives you the critical speed of the ball mill. So, what you would like to do is operate at about 20% or roughly 80% of omega c. That will be your operating point in order to ensure that you do not have too much happening by way of centrifugation. So, some of the industrial applications, ball mills are the most widely used size reduction equipment in industry. You go around, you will see that a lot of ball mills are used everywhere. As I have mentioned earlier, any size reduction process has low efficiency, which automatically means you have a high power requirement. You have to input a lot of energy to make size reduction happen, but it is an essential process in most industries you cannot do without. Again, just in terms of scale, you can see that the type of ball mills that are used in industry tend to be enormous, and they typically process tons per minute of material. So, very large quantities. Again, equipment maintenance is a huge issue in industry. You have to be constantly doing preventive maintenance and also replacement of parts in these ball mills. Some of the problems in conventional grinding, there is a lot of heat generation. As I mentioned yesterday, the excess energy that is input in order to do size reduction gets released as heat, and particularly in a ball mill you can have very high heat generation, and here is where again a wet mill has certain advantages in terms of being able to control and dissipate the heat release. You can have in a ball mill, you can build in residual stress. one thing that does happen is the surface energy of a particle that exits a ball mill is much higher than the surface energy of a particle that enters the ball mill. So, maybe sometimes that is good for your process, but frequently it is not. And similarly, there is a lot of residual stress that can make itself manifested later on. Micro cracking can happen. You may introduce very fine defects into the particle that you may not be aware of when the process first happens, but which can later on come and affect your process. It is difficult to handle hard materials, and so tool life tends to be low. How do you grind materials that are not brittle? For example, if let us say that you have a plastic particle or a plastic material and you are trying to size reduce it. As I mentioned, it is very difficult to do it because it is a soft material. So, a process that is used is called cryogenic grinding, where you take the soft material and you treat it with a cryogenic fluid which freezes it well below its yield point. So, you can convert a ductile material like a metal or a plastic or even a elastomer. By freezing, you can make it into a brittle material. So, by doing this, this process is known as freeze grinding. You initially chill the material so that brittle fracture becomes possible when you take it through the ball mill, and this can be done by using liquid carbon dioxide, liquid nitrogen, and so on. It has two advantages. Because the material is very cool to begin with, the heat rise is not a huge problem. It basically will bring it back to room temperature by the time the milling happens. And secondly, you can achieve the same size reduction with a significantly reduced force of grinding. Now, there are other types of mills, colloid mill, which is used to size reduce particles in a suspension or droplet size of a liquid that is suspended in another liquid. So, these are mills that operate at molecular level that can cause size reduction to happen in extremely small sizes. Edge mill, mortar and pestle, something you use in your kitchen. Some references. So, the last type of equipment is the ultrafine grinder. An ultrafine grinder can reduce size to the range of 1 micron to 20 microns. This table is not very visible to you, but you will see it when it gets uploaded in the course. But it is a very useful table that talks about the particle size and what type of size reduction equipment is appropriate for a particular particle size. So, it goes all the way from very coarse particles larger than 5 millimeters, where cutting and crushing are the processes that you apply, all the way down to the ultrafine and colloidal materials in the 1 to 20 micron range, where ball mills, jet mills are the most appropriate equipment. So, the fine grinding mills to produce ultrafine powders, the 4 that are most frequently used are hammer mills with internal classification, fluid energy mills, agitated mills, and colloid mills. So, in ultrafine grinding, clearly the particle size distribution is very crucial. The reason you are doing ultrafine grinding is to produce a very fine particle size distribution with good control. So, that you need to look at very closely. So, if you have a hammer mill that is used to make particles in the hundreds of micron size range, and you build it in with a particle classifier which segregates particles based on size, you could in principle operate it in such a way that the fine particles are continuously removed, the larger particles are recycled through the hammer mill and size reduced further. But how do you do that? I mean, you have to have a mechanism for drawing these particles and reintroducing them, and that is basically done using fans. The fans suck the large particles and put them back into the hammer mill. And by running this process continuously, this classifying air mill which combines this fan with a normal hammering operation can produce very fine ultra fine particles. And in this type of ball mill, the hammer mill, the particle size that you produce depends on the speed, the rotor speed, the size and number of vanes that are used for the hammer, and the volume of air intake, because that has an effect on the recirculation rate of particles back into the hammer mill. So, they can take 1 to 2 tons per hour of feed and get a particle size of 1 to 20 microns. The overall temperature remains low because of the airflow, which conveys the heat away, easy to clean. So, classifying hammer mills have a lot of advantages. A fluid energy mill is something very different in concept. You are entraining particles in a high velocity fluid flow. The primary mechanism here is particle to particle impact. So, you are accelerating particles to different velocities based on their size and density characteristics. So, the particles actually impinge on each other and size reduction happens. So, interparticle attrition is the primary mechanism here. They also have an inbuilt classifier, so that you can continuously segregate particles by size, remove the fines, and recycle the large particles. Another variation of the jet mill is a fluidized bed jet mill. So, fluid energy mills can handle large particles, but they are better suited to particles that are no larger than 100 mesh. They are used in many fine or precision manufacturing industries, where you require a very fine size and also a sharp particle distribution. The fluid energy mills, we used to have one in our lab. I think it is not operational anymore, but they do give a tight particle size distribution and good control over the largest diameter. But like with all size reduction operations, the control over the lower diameter is not as good. Agitated mills, again there can be dry grinding or wet grinding. What you try to do in an agitated mill is to introduce very fine vibrations, and the act of vibration itself causes size reduction to happen. So, if you have, by the way, there are vibrating mills also that we have not talked about, but if you have a surface and you have a particle sitting on it and vibrating, or the surface itself is vibrating, the micro abrasive contact between the particle and the surface can cause material loss and size reduction to happen. So, these mills use the mechanism of relative motion in a very small scale between the particle and the surface to cause additional size reduction to happen. Wet grinding, again, as I mentioned earlier, it is a good alternative to dry grinding, and again we do this a lot in our kitchens, where we are doing, wet grinders are very commonly used, has certain advantages and certain disadvantages over dry grinding. When you use a wet grinder for making very fine particles, you use a high velocity fluid stream, which introduces a shearing force to break apart agglomerates. And so, you can combine a wet grinder with a high shear module to produce extremely fine particles even in the submicron size range. All right, so these are just some references. What we have looked at so far is a very quick overview of various types of size reduction equipment that are used in industry. In fact, what I will try to do for the next class, there are some nice videos that show how these types of size reduction equipment work. There are also some videos that show how size separation equipment work. So, I will try to make the next class more of a movie show. I will try to get you some videos that you can look at. I think that is important for you to get a feel for how these processes really work in industry, because what you are going to see in the lab is not at all what it looks like in industry. So, hopefully these videos will give you a feel for how these equipment work in industry. Any questions? Okay, see you in the next class.